All right, thank you. Thank you for that kind introduction, and thank you all for making it to this virtual talk. So before I talk to you about all my work on fuzzing, we'll need to get on the same page about something, and that is that software still has bugs. And the reason I care about this, right, is because software is becoming increasingly pervasive throughout all different aspects of our lives, and so these bugs have increasingly severe consequences. For example, in the last few years, we've seen a number of pretty important security bugs like Heartbleed, Shellshock, Cloudbleed, all been caused by just basic logical correctness errors in programs. And behind the scenes, beyond these bugs that are so famous that they get logos and news stories written about them, I think we know from talking to folks that dealing with bugs is pretty expensive and annoying. In fact, some estimates put the cost of poor quality software at nearly $2.8 trillion in the US alone in 2018. So in my work, I try to help alleviate these costs, and I do that by building tools that help developers improve the correctness, security, and performance of software, with a particular focus on the problems that emerge when trying to scale to complex open source or even industrial scale software. And during my PhD, I focused on a particular class of these tools, and those are those tools that automatically find bug-inducing inputs in software. Now, what I really like about these tools is that they give you kind of a concrete input to look at that you can run through the program. And as a developer, you can get information about the dynamic behavior of your program and really pare down the kind of complex space of a program's control flow to the exact thing that's gone wrong. And that really helps you improve the quality of your programs. Now, with that in mind, what am I going to talk to you about today? First of all, I'll give you some background on the term fuzzing as I'm using it. Then I'll talk to you about a bunch of algorithmic innovations to fuzzing. And basically, in all three of these categories, finding performance bugs, exploring core logic, and improving random input generators, I've really focused on, small algorithmic improvements, simple algorithmic improvements that still allow scaling while not requiring too much tedious input from the user in order to increase the utility they can get out of these fuzzing tools. And after that, I'll get into where I see growing this work in order to improve the impact and breadth of my research. So with that, let me talk to you about what I mean by fuzzing. So the term fuzzing actually dates back, as you'll all probably know, right, to this 1990 CACM article by Bart Miller and others at the University of Wisconsin-Madison. And what they found, right, is that if you take a source of randomness and you generate a bunch of sequence of totally random, like garbage random sequences of characters, and you send these to these popular Unix utilities, eventually one of those sequences of random characters will actually cause a crash in the utility. And modern fuzzing techniques have, evolved beyond this kind of to target maybe deeper bugs in the programs, but they still bear some similarity to those core ideas of the 1990s fuzzing. In particular, the so-called fuzzer, there's some debate about when is it fuzzing, when is it some other type of systematic testing. But in general, what we'll see is there's kind of a somewhat random search element to the creation of inputs. And in general, those inputs are byte sequences. And what that means is we're going to test programs whose inputs are byte sequences, right? So either they get them via files or standard input or buffers. Now, the two types of there's kind of two big buckets of modern fuzzing that I'll talk about today. One is coverage-guided fuzzing, where the fuzzer is kind of this evolutionary feedback loop that generates new inputs via mutation. And the other is generator-based fuzzing, where you kind of have a handwritten input generator that's returning random elements in the search space. And this is characterized by tools like QuickCheck, CSmith, and it kind of appears naturally in a lot of other testing processes. Now, these brands of modern fuzzing have been very, very effective in finding bugs in practice. They've been applied widely across industry, like at Mozilla, Microsoft, and Google. And they've also been applied quite widely around open source. On the screen, I have huge lists of bugs that have been found by these modern fuzzing techniques in software that you probably use on a regular basis, including like Firefox and Adobe Reader, and of course, bugs in OpenSSL, which underlies all secure communication on the internet. Let me just, to set the stage, kind of zoom in a bit on how these algorithms are so effective at finding these bugs. So this coverage-guided fuzzing algorithm, sometimes there are other adjectives thrown in front of it, like gray box or mutational fuzzing. It's called mutational fuzzing because the way that it generates inputs is that it starts with a set of quote unquote seed inputs, so like reasonable files to the program. And then it generates new inputs by picking one of those seed inputs and mutating it. And these mutations are going to be like byte level mutations, things like adding and deleting random bytes and maybe setting them to interesting values like 0. The whole thing is called gray box in opposition to black box because those inputs are executed on a program under test, which is instrumented to give some feedback about what happened when the input was run through the program. And in particular, that execution feedback is basically the branches that are covered by the input. And the whole thing is called coverage guided because the algorithm will then save those mutated inputs, which covered new branches to its set of existing saved inputs. So over time, you're getting a set of base inputs that are more and more covering different behaviors of the program. Generator-based fuzzing, on the other hand, at a very general level, is just the idea that you have this handwritten human function that instead of generating just random sequences of characters, it's generating kind of random inputs within a search space. So on the screen, I have some examples of some kind of random looking XML documents that might be generated by an XML generator. Now, in spite of all their successes, there are some key drawbacks to these techniques. First of all, coverage-guided fuzzing, as you may be able to tell by its name, really has this fixed testing goal of increasing coverage. And that might be good for some general exploration, but it doesn't allow us to effectively find some types of bugs. And in the first part of my talk, I'll be talking about a new algorithm that we came up with that allowed this, that could effectively find performance bugs in software. The other big drawback, which it shares with random fuzzing, is it generates inputs via random mutations. And because of this, you get malformed inputs. That means that you won't be able to explore the core logic of a program as effectively, like say, the optimization stages of a compiler. And I'll look at different ways that we can smartly improve those mutation strategies in order to actually generate inputs which explore the core logic of programs. And finally, generator-based fuzzing kind of overcomes some of those issues, but it does require a lot of user effort to make a very super effective generator for a program under test. So in the last part of my talk, I'll talk to you about ways that we can allow the user to just write a very simple, random looking generator, but behind the scenes, we can learn distributions that make it more effective at testing and even program synthesis goals. So with that in mind, I'm going to start by talking to you about two papers. This is pervasive and Fuzz Factory. And the goal here was to find these kinds of performance bugs. Right, so typical fuzzing finds bugs that cause software to crash, things like segmentation faults, which are basically caused by a whole bunch of memory errors in C and C++, like null pointer dereferences and buffer overflows. But there are cases, right, where you're running a piece of software, it's running fine on most inputs, and then you actually do find one particular input on which the runtime or the memory usage of the program blows up. I think this actually happened to me on the program I had written to make plots for this paper, which is kind of ironic. And these bugs may not cause the program to explicitly crash, but they can still have pretty unpleasant consequences. In particular, if a deployed service has one of these performance bugs, and an attacker can send an input that kind of exposes that pathological performance behavior to that server, well, you can use up all the CPU and other resources of the server and cause a denial of service attack. So our goal in pervfuzz was to automatically generate these inputs with pathological behavior before any damage is done. And as you may have inferred from the name pervfuzz, right, we were wondering whether we could use fuzzing for this purpose. In particular, we were looking at this kind of coverage-guided feedback fuzzing loop where we save new inputs if they have certain interesting characteristics in their feedback. And you can think about how you might be able to use this kind of feedback-directed fuzzing to find performance errors. Maybe one of the natural things is to say, well, why don't I just keep track of the execution times of all the muted inputs I'm generating, and then save inputs that execute for longer, and keep doing this, and eventually I'll find inputs that cause performance errors. The reality, though, is that this turns out to be a little too coarse-grained to actually find, the worst-case algorithmic performance of some programs. So to show you why this is, we're going to take kind of a deep dive on a program called word frequency. And its goal is to count the frequency of words in a string. So for example, the string, the quick brown, the dog, has 4 unique words, and the occurs twice. So quick, brown, and dog occur once, and the occurs twice, right? That's the word frequency of this string. And one way to implement this program is shown on the control flow graph on the right. And this is basically a control flow graph for a linked list hash table implementation of this thing, where you go over all the words and words, you hash each word. If there's an entry in the hash table with that hash, you traverse the linked list until you either find that word, or you have to create a new entry for a new word. Now, the reason we're talking about this particular implementation, this is actually the implementation of this program that was used in Fedora Linux. And if you remember your algorithms 101 or 102, right, the worst case behavior of a linked list hash table is quadratic. So we want to take kind of a deep dive to understand how we could find the worst case performance behavior for these types of programs. And for that, we really need to kind of zoom in on a finer granularity at the performance response of this program under different inputs. And for this, I'm going to highlight hit counts to a few of the control flow graph edges in this control flow graph. So a usual case input, like the quick brown, the dog, it will hit this A edge, which corresponds to creating a new entry 4 times. It will hit the B edge, which corresponds to having to traverse the linked list hash table once, because the word the has the same hash as the other word the. But since it's the same hash, then it only hits the D edge, which corresponds to incrementing the count for an existing entry in the hash table. On the other hand, if you have an input like this one, like let's pretend this is an input that has all hash collisions, then what you'll see is the B and the C edges, which correspond to traversing the linked list hash table, are executed almost a quadratic number of times, like 21 times in the input length. So very different looking of the edges to hit counts map. But the A edge, which corresponds to creating a new entry, is not really hit that many more times. And what if we were in a case where creating a new entry was actually really expensive because we had some sort of bug in our constructor or something? Well, in that case, we might be interested in finding this last input, which executes the A edge the most times, 12 times for 12 very, very small words of length 1. OK, so with this in mind, we can ask ourselves, right, how can we consistently find inputs that have this worst case performance? And I'm going to kind of highlight here these maps of these edges to these hit counts. And how can we make sure we consistently find these kind of worst case performance? Well, if you look at them, really the worst case from, say, hash collisions is that there was those particular edges in the control flow graph that were hit a maximal number of times. And so what if we actually have an algorithm that maximizes the hit counts to each of these edges independently? then we should be able to consistently find these inputs as opposed to getting stuck in minima. And this is exactly what we did in pervfuzz. Instead of looking at coverage feedback, we instrumented the program so it would keep track of the exact hit counts to each edge in the control flow graph. And then we saved inputs that maximized the number of hits for some edge, right? So if you hit edge A 4 times or like 400 times and what you saw before was 3, either way, you save that input. And then you choose to mutate inputs that maximize the hit counts for one of those edges. And what we found is this actually effectively found the true worst case. Compared to prior work, which just tries to maximize a single objective, the path length through the program, that prior work for this linked list example only found inputs that had a lot of very, very small words. It did not find the true hash collision case. On the other hand, pervfuzz consistently found inputs that basically what they did is they, first of all, inserted a very small word into the hash table. Then they inserted a bunch of words that hash collided with that input, putting the entry for the first word at the very end of the hash table. And then they caused lookups of that last entry in the linked list many, many times. And we consistently find this kind of worst case. And even if we're maximizing all these different objectives, it turns out this still scales to larger inputs. Like, for example, we found an exponential runtime error in the parser of the Google Closure compiler for JavaScript.
So I'm not sure if these next slides answer the question, but there is a question from G. How do you know that what edges are some interesting edges a priori?
So it turns out that usually edges kind of, there's kind of groups of edges that will be naturally related to different kind of performance behavior. And eventually what will happen is that, so even if you have many of them, even if you try to maximize all of them, it turns out that you're still kind of okay. We have some other metrics of trying to make sure that if you have an edge that like you haven't been able to increase the hit counts of in a long time, you no longer prioritize that one. So that's one tactic to deal with that. Yeah. I can't see the chat, so please do let me know.
Yeah, I'll read the questions when I see them.
Okay, great. Thank you for that question. So the other thing I want to highlight about this is I've been talking about edges and hit counts to those edges and maximizing those. But in reality, there's no reason this algorithm shouldn't work in the more general case, where you have an objective that's kind of characterized by a key value map, where you're trying to maximize the values for some keys. And this is exactly what we did in Fuzz Factory. So in Fuzz Factory, we actually made this generalization much more explicit. We made it easier for actually users to be able to inject calls into the program that constructed these key value maps automatically. And this also allowed us to kind of compose different goals. So you could not only be trying to maximize, edge hit counts, but some other type of key value objective. I'll show you an example in a case study. So say that what we want to do is find memory usage bugs. So, like out of memory issues. Well, what you can do is keep track of the memory allocation locations as keys. So all the mallocs in your program. And then you try to keep track of the cumulative amount of memory allocated for at each of those locations. And if you have a memory leak, right, eventually trying to maximize the memory allocated at some location should find it for you. And indeed, it turns out if you run this on a bunch of benchmarks, on the x-axis, you have some different benchmarks. On the y-axis, you have the maximum amount of memory allocated. And what we see is that compared to just basic gray box fuzz, coverage guided fuzzing in the blue, the orange bars are, which represent the amount of memory allocated with this kind of trying to maximize those allocations, right? It's higher. So that's very interesting, but there's actually on one of these benchmarks where the coverage guided fuzzing finds a higher maximum than the other one. And we're wondering why, and it turns out it's because this particular benchmarks has a lot of hard comparisons. So basically this means like if conditions where the input is compared to a long fixed sequence of say like 8 bytes long. Very difficult for mutational and random fuzzing to get through these comparisons. But it turns out that problem of getting through comparisons, you can again cast as this maximization problem, right? You can keep track of all the locations in the programs where you have these hard comparisons and try to maximize. And then if you try to maximize the number of bits that are matched in each of those comparisons, you'll slowly generate inputs that eventually, maximize that maximize the number of bits matched and satisfy the equality condition, right? And this is one of those cases, right, where you'll see that at some point the maximal value will round out. And actually, it turns out that if you compose together, if you say like you're both trying to get through these hard comparisons and maximize those memory allocations, you do better than the sum of its parts. And we were able to consistently find these memory usage bombs in libpng and libarchive, which are already heavily fuzzed open source libraries, including, for example, in libarchive, a 20-byte input that causes a 4 GB allocation. And that is much beyond the compression ratio of these systems. So the key takeaway here, right, is that we can generalize this kind of fuzzing algorithm to this more multi-objective space and really allow users to find their own kind of custom bugs. PerfFuzz actually got a distinguished paper award for this work, and Fuzz Factory, that generalization, every time I speak to industry folks, they're always really interested in being able to kind of customize their feedback to their use cases. Okay, so with that, I want to get to the next branch of my work, which is this problem of exploring the core logic of programs. And I'm mostly going to talk about FairFuzz in this work, in this section. Now, if you look at a lot of the programs that we fuzz, they typically have an input validation stage and a core logic stage. For example, syntax checking in your compiler, and then core logic that actually, performs optimizations on the IR.
So,
and
yeah. To continue, there is a question from House. Can we also fuzz the objective function to find a good objective?
Can we fuzz the objective function to find a good objective? It's going to be, we're going to have to use maybe some more like mathematically sound approaches to fuzz there, because, right, like you can fuzz in a certain objective and it relies on the search algorithms being effective relies on being able to run many, many inputs quickly, right? So now if I want to fuzz the objective itself, each of those steps is going to be much longer, right, to figure out if I have a good objective. So I'll probably have to do, like when I'm trying to figure out my objective function, if I want that to be effective, I'll probably have to be a bit more strategic about how I'm searching through the spaces of objective functions than just randomly, mutating objective functions. Does that answer the question?
Yeah, thanks.
That would be one way to do it. Okay, so speaking of getting, of finding better objectives and finding more bugs in the program, there's this problem that most of the bugs that we find with random fuzzing are mostly in the input validation stages of programs. So, so you tend to find bugs, in your syntax errors rather than, in your optimization stages. And the reason for this, which I've mentioned before, right, is that kind of because of how we generate new inputs, which is via byte level mutations. So for example, say you're fuzzing a program that takes in inputs that are XML. I'm going to use the XML example kind of throughout the talk to keep it simple. You might have to make sure that all the tags in your XML document match. So even if you have an input whose tags match, like foo and foo, if you just mutate this by randomly, copying some bytes around, the likelihood of the mutated input still hitting that branch that requires that the tags match and getting through the input validation phase is getting much lower. So this is a problem because we're just testing input validation. Now, what we tried to do in FairFuzz was figure out a way to restrict the space of mutations so that many more of the inputs you would generate would, keep kind of some of that core structure that was required to get into the deeper parts of the program. In particular, what we say is we look at a program and we figure out a branch to target. For example, the true branch of, the tags matching in a fuzz input. That's probably rare. It's probably hit by very few fuzzer-generated inputs. And then we also assume that we have at least, one of those reasonable looking seed inputs actually still hit that rare branch. And now what we want to do is figure out where we can mutate this input and continue to hit that rare branch. And for that, it turns out that in between the tags, right, the text that's in between the tags, you can still mutate that and hit the rare branch. And now, instead of mutating totally randomly, you're going to mutate with this branch mask so that you're only touching those middle bytes. And the likelihood of these mutants still satisfying that condition is much higher. Now, of course, the difficulty here is that it's getting this information about the branch mask, about which bytes you can mutate, right? There are 256 options for each position. So it seems like it would take a long time to compute that. So what we did in FairFuzz was come up with a good approximation for this. And basically the way we computed this is that we looked through the input and we went through the input and we flipped each byte. And we said, hey, if I flip the first byte of this tag, do the tags still match? And in this case, no, because you mutated the tag. So you mark that byte as not OK. And you keep going through the input, you're mutating each character, seeing if it still satisfies the rare branch. And if you get to some point where you can actually mutate the characters and still satisfy the rare branch, you mark those positions as OK. So basically, we do one flip for each position in the input. And then we can summarize that information in an approximate branch mask. So this is exactly what we did in FairFuzz. Basically, we again have this coverage guided loop. The thing we changed is that we pick inputs to mutate if they hit one of these branches hit by very few fuzzer generated inputs. And during fuzzing, before we mutate inputs, we compute this branch mask, generating all those flipped bytes. And then we generate new mutants with this branch mask. And overall, what we found is that FairFuzz exceeded or at least equaled the coverage of kind of state-of-the-art fuzzing. And it achieved up to 10% increases in branch coverage, especially on benchmarks that had highly nested structure, like lots of if statements within if statements. And kind of because of the fact that, this approximation was still pretty effective and that it didn't actually change the objective function, it was very easy to use. And because of that, a lot of folks have built on it in the fuzzing community. People have asked for it to be integrated in kind of the state-of-the-art coverage guided fuzzer, AFL++. And when folks have asked, what should I do as best practices in my fuzzing, experts have suggested that you should definitely use FairFuzz as one part of your fuzzing deployment. So FairFuzz is very nice. It's like it's a nice example of what you can get by just mutating the algorithm without requiring much more from the user. But the natural question here is like, if we can actually get more information from the user about the structure of valid inputs, can we do better? And it's at this point that that second branch of fuzzing that I talked about, generator-based fuzzing, comes in. Now, generator-based fuzzing is very effective, but one of the key problems is that it kind of requires our input generator to be very good. We don't really have a natural way of closing the feedback loop and telling the generator that it does a good job or not, in part because we can't really easily mutate the generator-generated input, which was what we relied on in order to close this feedback loop in coverage-guided fuzzing. So to kind of talk about the innovation here, I'm going to have to look at a generator in more detail. And again, here's a very simple generator for XML. You take in a source of randomness. You'll randomly choose a tag for the current element from some set of tags. And then you'll randomly choose some number of children for that root node. Then you'll go through, you know, for 0 to the number of children you choose and add a child. You can randomly choose to randomly add some random text. You could do other things to like randomly choose a number of attributes and add them. And in the end, you'll return this XML node. Now, we could require users to, you know, along with the generator, write a mutator that tells us how to mutate inputs to keep them well structured. But to me, I didn't see mutators emerging as naturally from users as generators do. So instead, we kind of looked at what we can do with just this information. And what we noticed, which is maybe obvious because I've put random explicitly as a parameter here, right? But the generator has kind of imperative or functional code that's creating the element. And then you have kind of these random choices in the tags or the number of children that are actually affecting what the generated inputs looks like. And it turns out you can actually hijack this in order to get mutations for free. Why is this? Well, if you think about it, this source of randomness that's being massaged by these random dot choice operators and whatnot into integers and strings that are used in the final generator generated input. Really, that source of randomness, once you've seeded it, right, it's just an infinite stream of random numbers that, you know, next int will just then be using into a modulo in order to get an integer within the range you want. And really, if you think of it, like an infinite stream of numbers is really just a stream of pseudo-random bits, at least when, you know, you're using int 32s. And then the interesting thing, right, is that once you fix one of these sequences of pseudo-random of these bits, each of those sequences directly corresponds to a single generator-generated input, right? In this case, this particular XML tree, which is serialized as follows. And then the interesting thing is if you mutate some of these bits that are influencing the choices, you'll get a slightly mutated generated input. For example, if you change bits that were consumed by the random operator that chose the tag for the root node of this XML document, you will actually get an input that now modifies the tag of the root node of the XML document. But unlike, you know, a byte level mutation, it does this evenly in a manner that's still structurally sound. So this is the key observation that we leveraged in Zest. Basically, what we did is we took that generator, which now we think of as taking in this sequence of parameters rather than a source of randomness. And we kind of replaced the thing we're mutating in the coverage guided loop to be those parameters rather than the generator generated input. And the really key thing you get here is that now you have this coverage guided fuzzing, but you're conducting mutations at a level that's actually structurally sound. So you'll be searching through the space of semantically valid, at least syntactically valid inputs. And along with some other tweaks to the feedback, which I'm happy to chat more about later, we were also able to search through the space of semantically valid inputs to these programs. For example, on the slide, I have an example of a JavaScript program, which, unlike the one I showed earlier for pervasive, is actually syntactically valid. There's some while loops, and then there's a var statement after some breaks in the while loops. And it turns out that when you pass this input to the Google Closure compiler, you do not get a syntax error, but you do actually get an exception during optimization. And it turns out that that exception underlies a correctness bugs in the optimization stages. Because JavaScript is a very strange language, and it turns out that var statements are hoisted. So even if they occur after a break statement in a loop, you cannot delete them in your dead code elimination stage. Right? And this is a type of bug that generator-based fuzzing alone with a simple JavaScript generator was not able to find in an effective amount of time. And coverage-guided fuzzing that was just mutating things was not able to generate such semantically valid inputs. So in both of these cases, we saw how better increasing by improving the mutations of this coverage-guided loop, we could actually explore the space of the core logic of the program. And Zest actually won a Distinguished Artifact and Tool Demonstration Award for this work. I'll pause for a few seconds here in case there are any questions.
No, I think so far so good. So we can probably move on and keep questions again.
All right. So the reason I had to talk to you about Zest, beyond it being very cool and actually finding bugs in the core logic of the programs, is because I became very interested by this idea of random input generators in the last part of my work. And I'm going to talk to you about RLCheck, which is again about testing, and AutoPandas, which is actually in the domain of program synthesis. So we have this problem with generator-based fuzzing in that we don't want to spend, I don't want users to spend too much time tuning this generator exactly to their program under test. But if they don't, then not all the inputs that are generated by the generator are interesting to the program under test. Like consider again, we have a general XML document generator, but our program only accepts inputs that have a given schema. So for example, the Maven schema requires that your first tag at the root of your document have the tag project. And even if you're choosing from a fixed set of tags, the probability of that happening is like 1 over tags. And if tags is something like on the order of 100, right, this is already pretty small. And the problem gets worse because then we're going to recursively call this generator to generate the children of this root element. And again, you'll get into the situation where, for example, there's only a subset of tags that are valid, like dependencies is valid, but the dependency doesn't fit the schema. And because of this, like quickly, the probability of generating a valid input, is going to be less than, the product of all these valid subsets over the tags to n, which is basically going to be proportional to 1 over x to the n, which goes to 0 quite quickly. Okay, so this is why, generator-based fuzzing alone, if our generators aren't super well tuned, might not get too far in testing. Now in Zest, we saw that, one way of seeing it is that you're using these generators to get these higher level mutations. Another way of seeing it is that you have this random input generator, and then it's backed by this whole complicated coverage guide fuzzing loop, and it's no longer really random, right? It's taking in those parameters that we're mutating. But what I asked myself is, why should we just restrict ourselves to that particular kind of backing? And that's what we tried to do in our RLCheck. Basically, we were wondering if instead of having this whole coverage guide loop in the background, we could actually directly control the choices of this generator. And let me show you what I mean. Right, so you have a generator that there's some calls to random, and I want the generator to still look like this to the human that's writing it. But then what I want to do is behind the scenes, I want to tweak these distributions so that instead of just returning a random tag, they're returning the tag that will maximize the chance of generating a valid input further down the line. Now, this is a challenging problem, finding these distributions automatically, in part because they're actually not absolute distributions, right? The best tag or the best choice at some point in the generator really depends on the context of that choice, right? I told you, the root node, the best choice there is the tag project. But if you're the child of project, there's another subset of tags that are relevant. And if you're the child of another child, then there's another subset of tags that are relevant. So in order to solve this problem, we're going to have to come up with some notion of context. And here I've illustrated the context as, the XML DOM tree we're generating so far. But we wanted to come up with a notion of context that was a bit more general. So at its base, right, we're going to have to add context as a new parameter to our generator. And now the question is, what information can we have that's kind of generally available for all these random input generators that kind of captures what the input is so far and would allow us to, learn what the best choices are. And what we decided upon in RLCheck is that, well, the sequence of choices we've taken so far kind of uniquely captures the input we're generating. right? So we're going to keep track of all the choices we've taken in this generator. And then the context for a particular choice is going to be basically all the choices that we're taking in the parent recursive call. And we manually added this to the generator, but you could do this programmatically quite easily. And then, of course, right, we need to pass on this context of all the choices that we're taking to the parent into those calls to random. Now, what we notice is we now have the following problem. We have a choice space, right? So at each point in the generator, we have some choices we need to take. And then we have some context for those choices, which is kind of the sequence of choices that have been taken so far. And how do we solve this problem? So there are actually a few different ways of doing this here, but one of the things we were thinking of is, well, you know, this kind of sounds like we're in a given state, right? We have a given context, and we need to take the best action in that context or state, which is exactly the problem that folks are trying to solve with reinforcement learning. So that's basically the idea of RL check, is that instead of these calls to randomness, those calls to randomness are actually replaced by calls to, you know, an RL guide that provides the same interface as the choice of randomness. But behind the scenes, instead of choices being taken randomly, they're being taken such that the agents are learning through time, you know, what are the best choices to take. And we rewarded those agents with a pretty high reward if the input they generated was not only valid for the program under test, but also unique. And to be clear, we did try to use deep learning. I could talk about that later. But the thing that ended up working was a very simple, just table-based Q-learning, looked at the last K elements of context. And the nice thing about this is that you don't need to pre-train it. So you can just learn these better distributions on the fly as you're testing. And the other nice thing is now we're back in the case where we don't actually need to instrument the program in order to get coverage feedback, because we're just looking at whether the inputs are valid. And we can get that via, you know, just return codes from the program. And here's a graph showing how it works. On the y-axis, you have the number of unique valid inputs that are being generated by each technique. And what we saw is that RL check was able to generate orders of magnitudes more unique valid inputs on, say, this Google closure benchmark than either quick check, just like regular generator-based fuzzing, or Zest, which is the more sophisticated method I talked to you about earlier. And this pattern of order of magnitudes increases was repeated over most of the Zest benchmarks that we evaluated this thing on. And this was very exciting to me because, you know, it's kind of just like basic table-based reinforcement learning. And that's just one way to learn these distributions automatically. Maybe not the best ones, but we already see really, really promising results. And it also got me thinking that we now have this powerful tool where we kind of have this abstraction of random input generators, and we can guide them more smartly. And maybe there are other search problems we can solve. And I'm happy to talk more about this after. But the problem that one of these classic search problems, right, is like input-output based program synthesis. So we have an input-output example where the user has, in this case, there's a table that's kind of wide, and they want to kind of collapse 2 columns into 1 column. That's the program they would like to perform, but they don't know how to write that program. So our goal is to find a program such that when you run it on the user-provided input, it gives you the user-provided output. And in AutoPandas, we explored doing this via a generator-based search methodology. In particularly, what we did is we created a generator of pandas programs. These are programs that consist of a sequence of API functions in the pandas library, right? So you choose a random sequence of functions. For each function, you choose some random arguments. And the IO examples we have are kind of this table transformation domain. Then basically, we'll call the generator, get a random program, run the program on the input. Ask ourselves, did that do what we wanted? Did it give us the user-provided output? If it does not, then we say, OK, let's generate another random program. And we'll try again, and again, and again, until we finally get a program that matches the intended output. Now, the neat thing about this is that we just needed to write this program generator to capture the search space of programs. And this was very handy because Pandas has over 100 API functions that we supported, and each of them have kind of complex constraints on the argument space that are much easier to talk about if you can just kind of write an imperative program that can even directly call the API you're trying to generate programs in. Of course, the thing you'll be asking is there's no way that this works if I'm just generating random programs, right? No way that it scales. And that's kind of true. And so that's why in AutoPandas, we again had to rely on this fact that the generator looks random, but in the back end, it's doing something much smarter. Basically, what's happening is that, remember how in our LCheck, right, we had like a context that was an additional argument to the random choice. What we do in this case is the additional argument to the random choice is an abstraction of the specification of the input-output example. And we've actually pre-trained those random choice operators with a graph neural network that takes in a graph abstraction of this input-output example and learns distributions over, what is the best argument to choose, or what is the best sequence of API functions to choose in order to get a program that looks like it might be able to do this input-output example. And this was actually able to scale to real-world API uses, including sequences of at least 3 API function calls, which is quite significant given that there's hundreds of different API functions that we were supporting. And what we see in both these cases, right, is that there's real power to having just this abstraction of the random input generator, which kind of naturally emerges in some of these cases. And for example, in AutoPandas, we're now able to do some program synthesis without requiring someone who's necessarily an expert in program synthesis, but just can write a generator of the programs they're interested in searching through. So I think I have enough time to wrap up here and then get to questions. A lot of the things I've talked to you about today are these kind of algorithmic improvements in fuzzing or test input generation more broadly. But it is the case, right, that even though we have these powerful tools, not everyone is using them to improve the quality of their programs, right? And the question is why, right? There's a lot of reasons why. People are lazy, but there's also a lot of challenges to being able to run these tools. For example, if your program under test is not a command line utility, how do you write a test driver that accepts a byte sequence and actually exercising interesting code? This is not a trivial problem. Or if I have a program which really expects more structured inputs, now you expect me to write a grammar or a generator. And even if I tell you write a really simple generator, I know from talking to folks that that upfront cost seems a little uncomfortable. And then you have this kind of higher level problem of, do I even care about the bugs you're generating, right? Are these inputs too strange? You're not really helping me fix them. Like, what is going on? So one of the big directions I see that needs to be pursued and that I want to pursue in order to increase the impact of this work is to, focus on all the problems around fuzzing and test input generation, right? Like automating the test drivers, inferring input structure, even looking at, what kinds of, maybe patch information can we provide developers so that these bugs are a bit less onerous to deal with. And I know these are this is a very powerful space to work in. And there's a lot of interesting problems that emerge there because I actually started dipping my toes into this during my internship at Google, where I helped lead the development of the Fudge tool. And what Fudge did is it automatically built test drivers for libraries that exposed a public API, but did not, have a corresponding command line utility that we could easily fuzz. And solving that problem, required pulling from ideas in scalable static analysis, in random search, and even in HCI, because in the end, it was simpler to build a UI that allowed developers to kind of see what are the different test drivers are available, which ones are good, which ones might provide new coverage of my library. And this ended up with over 200 of these automatically generated drivers being integrated into open source projects. And that alone resulted in over 150 security improving fixes to these projects, right? And this is a big advantage even without having to refine our fuzzing algorithms further. So that is one big space of expansion that I'm going to target next. And then finally, to kind of think about where we're going in the long term, there is kind of this elephant in the room that all of the programs, this maybe goes back to Ola's question about, can you fuzz the objective, right? The programs that we can fuzz are generally kind of, single-threaded, deterministic, and fast-running programs. And the reality is that's just a small slice of modern software, right? If you think of the complexities of distributed systems or mobile applications or machine learning or probabilistic applications, these programs are not necessarily like fast running. And more importantly, the abstraction that we have in fuzzing, which is a single test input that shows a bug, right? The nice thing for a program that's mostly control flow heavy is you can then run the program on the bug. You can look at, oh, what you did wrong was this loop wasn't working correctly. And you can find out what's going wrong. That's not the case if you give like a neural network. You say, oh, this cat is, it turns out that this like cat is classified by a dog as your network, or this pair of inputs are behaving unfairly. You can't just look at those inputs and improve the quality of your network. You need a different kind of abstraction to provide developers. Maybe something like a summarization of all the kind of sets of inputs on which the network is behaving wrong or unfairly. And what I want to do going forward is collaborate with folks on new notions of these artifacts that will be just as useful as test inputs for these new systems. So today I talked to you a bunch of algorithmic innovations, ways that we can really extract more effectiveness out of these fuzzing algorithms while just using minimal feedback from the user. And going forward, I first of all want to make these algorithms more accessible to all the code where they really can have an impact by focusing on the breadth of problems that need to be solved in order to apply these fuzzing tools to more and more programs. And then, I want to keep collaborating with folks that are expert in these kinds of, new notions of programming, or maybe not new, but different notions of programming than what we look at in the fuzzable space, and come up with new artifacts that can really be as useful to developers of these systems as test inputs have been in traditionally fuzz systems. So that's my talk, and I think we still have some time for questions.
Oh, thank you very much. That was a great talk.
Thank you.
So, you're ready for questions?
I have a question.
Yes.
Thanks for a great talk. You at the end you said how you would like to extend these ideas to say distributed systems or more complex programs that are not necessarily single-threaded and deterministic. But if we just stick to the single-threaded deterministic space, what are classes of bugs that you hope RL can find, not RL, fuzzing can find, but it cannot right now? I mean, you had this challenge of all the bugs being in input validation versus core logic, and you wanted to push them deeper into the program. But are there still classes of bugs that maybe other techniques find, like symbolic execution, that fuzzing is unable to find? And can we categorize those?
That's a very good question. The challenge of what kind of bugs can fuzzing find, it's always kind of difficult because it kind of depends on the entry point to your, it depends on the entry point and it depends on the oracles you have, right? So you need a test oracle. That's why we mostly find these memory usage bugs. In orders of can it actually explore the inputs that would reveal those bugs, right? If your test driver is small enough and you're in a small enough unit, then you will be able to find it. But maybe you could also find it with symbolic execution. So I don't know, maybe the greater problem is that maybe the greater problem is kind of figuring out ways of, helping users write oracles that are relevant to the different testing problems they have. In Fuzz Factory, what we did was kind of let users insert feedback into the program where basically they say like, if you get into, I want more inputs that get into this part of the program. So you basically say like, at this point, set this key to this value and try to maximize it. And that's how you explore more of those types of bugs. So the notion of the depth of the bug is very, very related to the fuzzer that's trying to find the bug. Like it's kind of how it's defined. So I think when we're talking about finding different types of bugs, it's really going to be about, helping folks write oracles that are, or, write models of bugs that are more relevant to them. And then, yes, then we might have to, if we really want to get from an input that's like starting at the start point and gets deep in the execution, then we might have to leverage, kind of component-based fuzzing or component-based symbolic execution to be able to actually get into those deep paths.
I see.
Yeah.
I also had a question. So yeah, thanks a lot for telling us about this work. It's really interesting. For the reinforcement learning bit, if I understand correctly, you were saying that your setup kind of has kind of like a binary reward, like you're trying to reward things that are unique and that are also valid. So do you think there might be interesting things to do there with like a quantitative reward, or are there kind of obstacles to kind of experiment with the kind of reward?
By quantitative, do you mean like one that ranges that's not binary, or do you?
Yeah.
Okay.
Yes.
Yeah. So it's like, it was actually like a ternary reward, but similar. It was like 0 if it's invalid, 1 if it's valid, but I've seen it before, and like something else if it's, that's definitely an underexplored part. There's, right, like you could, it's kind of a trade-off. So something you could do if you had gray box information, but then maybe you should just do gray box information is, right, if you have some information about maybe how far you've gotten through the program or through the checking, right, you could imagine having kind of a sliding scale reward that might be better there. The challenging thing also with like reinforcement learning as a class of algorithms, right, is that our rewards aren't stationary, right? Like I don't really want to just tune my generator to always give me the same valid input over and over again. So that's another big class of challenges in the reward structure, but it might be almost, that might not just be, that might be an issue that we can maybe look at kind of an RL inspired algorithm, but we're going to have to do something different there. I know there's been some work in looking at least for like Android testing and trying to use these notions of curiosity for reinforcement learning. But in the end, that kind of just ends up being kind of like, have I seen this path before? So yeah, there's definitely a lot more work to do in that space. Yeah.
Cool, thanks.
This is Tom. If you divide the program into input validation and core logic of the program,
yeah.
I mean, in some sense, the user has provided a specification of the valid inputs by the portion of the program that represents input validation.
Yeah.
So, have you thought about using that part of the code in order to
yes
be a generator of the kind of inputs that you want?
Yeah, actually that is that is actually some stuff I was trying to work on over the summer of, if you know what part, right, you kind of have a parser, it's kind of characterizing, it's kind of characterizing the space of valid inputs. Now, whether you can do this cleanly, it kind of depends on the types of programs you're targeting. I know that like there's some work there's some work called Beginner's Luck, where they basically developed a DSL where you can write both a checker, and that checker itself is a generator. So, so basically your input validation, like you have the same code for the input validation as for the generator itself. So you can, that is definitely a very good idea of doing it. It's a bit more challenging when you look at more general purpose programs where people write very strange parsing code and checking code. But yeah, it's finding ways of leveraging that in order to get those generators in the first place is something I really want to pursue.
I have a follow-up question on that. I mean, are you assuming white box or black box here? Because if you're assuming white box, for example, Andreas Zeller had worked on mining grammars from the beginning, and even for black box, I guess Alex Aiken had this work on learning grammars. So is the problem just that sometimes you don't have a grammar is the wrong abstraction, or I'm trying to understand where you see the difficulty here and where is the missing piece? What is the missing piece that is not there yet?
For me, the big missing piece is the scale of all those algorithms. So I've actually been with a student. We've actually been doing some work on black box grammar learning, and like, you know, the graded inferred grammars can generalize somewhat. But we actually found that even for like more straightforward but very recursive grammars, you know, they were generalizing them, right? But they weren't actually learning the core recursive structures. So yeah, you can generalize. You can write a grammar that, you know, you'll generate more inputs in the search space. But the big challenge is actually capturing the entire space of the challenge is having an abstraction that, you know, actually bounds all the search space of inputs. So there is definitely promising work in doing this, but it is still restricted to certain classes of grammars, certain classes of programs. So there's like, actually, it's, you know, you can't really run these and get a nice generator for PDF documents that you can actually use to fuzz things.
Yeah, I think it would be very interesting to theoretically sort of characterize what these sets. I mean, we know that grammars cannot be learned in general, so it would be interesting to actually understand what it is that these tools learn and don't learn.
Yeah.
Okay, so I think it's 3:03, and so I think we should. 3:03. I'm in the East Coast right now, so I'm
yes, I know. Yeah.
It's 03 somewhere. So I think we should end this, and I think all your meetings will be in these. Oh, somebody really did end this.
I think